So I'm Noelia. I'm a postdoc at the Australian National University, and today I'm going to present this talk titled I Want My Own Star Too. Hopefully, after listening to this, everyone would also like to have their own star. So let's go. Okay, sorry. Okay, there we are. So this is me. I was born in Spain 29 years ago. I studied industrial engineering. My specialty was electronics, and I got 2 professional positions as an engineer, first in the European Space Agency in the Netherlands, and then in the Astrophysics Institute in the Canary Islands in Spain. In 2016, I started my PhD in astrophysics instrumentation, so just building something. I finished October last year, right before moving to Australia to become a postdoc here at the ANU. Okay, so what do all these pictures have in common? Well, they show lasers that we're going to use to create our own stars. And this is what we call laser guide stars. Laser guide stars are artificial stars that we can generate wherever we want in the sky. So in order to understand what a laser guide star is and how this works, we are going to start our journey by the beginning. So just wondering, as Brad said, why do the stars twinkle? Well, they twinkle because we look at them from the Earth, and our eyes and our telescopes are surrounded by the atmosphere. So the light coming from the stars is perturbed by the atmospheric turbulence, and that's why we see it twinkling. So this affects our astronomical observations, and instead of seeing sharp and nice resolved objects, we see blur things like this. Or we cannot really resolve objects that are really close because they are really bright and the atmosphere makes them blurred. But this not only affects astronomy, but also affects space applications, all of the ones related to sending or receiving light from a satellite or from an object in space. So this is the case of optical communications. Optical communications consist of sending or receiving information using a laser from the Earth to a satellite or from the satellite to the Earth. So because this laser will have to travel through the atmosphere in the same way the light coming from the stars, this atmosphere is going to perturb the laser light, and we are going to lose some information. Also, when we try to observe an object in space, like a satellite or a piece of space junk, we are not going to be able of seeing what we are looking at. We are going to see this kind of blur thing. But what if we could actually change this and remove this negative effect? Well, in that case, we could see like much better objects like this one, or we could actually resolve the center of the galaxy, that we see in this animation. Or actually, we could even look at the satellite and identify which one it is the one that we are looking at. So in order to do that, we need what we call adaptive optics systems. Sorry, this has like stopped. Okay, sorry. Yes. Okay, there. Adaptive optics systems, sorry. So these are systems that measure and correct the atmospheric turbulence and remove the negative effect on the light. So how do they work? Well, we have our telescope capturing light from a reference object on the sky. This light will have to travel through the atmosphere and will get perturbed by this atmospheric turbulence. We'll go all the way to here, to our sensor, or what we call wavefront sensor. This sensor will measure the atmospheric turbulence. We'll send this information to a computer, and this computer will send some commands to a corrector element or deformable mirror. This element will change the shape to adapt to the perturbation that we are measuring. So it will be something like this. So we have our deformable mirror, the light coming from the object with the atmosphere would be like this kind of blur thing. But then we are going to measure it by the wavefront sensor, send information to the deformable mirror, and this will change the shape and get a much nicer image on our science detector. So in order to do this, our wavefront sensor needs a reference object on the sky to measure this light. This reference object can be the object that we are observing, but usually this object is not bright enough. So we need to put another object close to that, or we need to use another object close to that, whose light we will be able of using with the wavefront sensor. So the reference object needs to be closer to the object of interest, because otherwise the light will pass through a different amount of atmosphere. So as a reference object, we could use a natural star. But believe it or not, there are not enough bright stars on the sky. And yeah, I also say like, nah, that's not true. But yeah, it is true. There are not enough bright stars. So, but why worrying about this if we can actually create our own stars? So let's generate some stars up there, wherever we want. And this is why we use laser guided stars, to create a reference on the sky to measure the atmospheric turbulence with our wavefront sensor in the adaptive optic systems and correct for this atmospheric turbulence. So by looking at this image, how many colors, or which colors do you think we use in these lasers to generate these stars? Exactly, green and orange. So we are going to continue our journey by explaining now the two different types of laser-guided stars that we can create. So let's start by the green one. We have our telescope here, we have the atmosphere with all the turbulence, and these circles represent the dust particles in the atmosphere that are flying up there. So, okay, we have everything ready, we have set up our system, we press the button, and boom! Well, hopefully it won't explode if we have done everything properly. And we will see just a green laser beam coming out of the telescope. Something like this. But why do we actually see this? Well, because the laser is reflecting on each of the dust particles in the atmosphere. That's why we will see the green laser beam from the exit of the telescope to the upper part of the atmosphere, which is going to be around 20 kilometers above the Earth's surface. Below that 20 kilometers, we won't see the laser anymore, because there are not going to be any more dust particles in which the laser will reflect. So this reflection on the dust particles are called the Rayleigh return. But okay, wait a minute. We need an artificial star, or something with a star shape. Now we have a line or a cone of light. So we have to tell our wavefront sensor, our camera, to only capture a certain area of that cone of light. Otherwise, we won't have the star. So we need to tell the wavefront sensor, okay, we have our Rayleigh laser guided star, is what we call it, here, or here, or maybe here. So where we could put our Rayleigh laser guided star? We actually wanted to put it here. So the higher in the highest in the atmosphere as possible, because we are going to use that light from that small area to measure the turbulence. So that light will travel downwards from that illuminated area to our telescope. So if we select the area in the middle of the light cone, we are going to miss all the turbulence information above that area. So we wanted to have our Rayleigh laser guided star as high as possible. Okay, so this was our first type, the one that we call Rayleigh laser guided star. Let's go now to the second one, the one that we use an orange laser for this. So again, we have our telescope, our atmosphere, and now we have a third element, the sodium layer. So this is a layer full of sodium atoms at approximately 90 kilometers above the Earth's surface. So again, we set up our fish system, we have everything ready, push the button, and what we get is the same as before. We are going to get the Rayleigh return first, because we are going to launch our laser, our orange laser now, and this laser is going to be reflected on the dust particles of the atmosphere. So we are going to see this Rayleigh light coming out of the telescope. Then after that, once the atmosphere is sober at around 20 kilometers, we are not going to see any more the laser, but something will happen up higher above the Earth, because the laser will keep traveling up, and then it will reach the sodium layer. So at this point, the laser will excite the atoms in the sodium layer, and those atoms will glow, generating our nice sodium laser guide star at 90 kilometers above the Earth, in such a way that we will be able of measuring the whole atmosphere volume below this 90 kilometer sodium layer. So this would look like this, and this is a real image taken in Chile in 2016. So we first could see the Rayleigh illumination of the dust particles in the atmosphere by this orange laser. Then we will see the dark area a bit up, where we don't have atmosphere anymore. And then we have our tiny, cute laser guided star up there. And then we also see Saturn here. So in this scenario, we will have our telescope like here, and then we will be measuring the atmospheric turbulence from our telescope to the sodium laser guide star. So our telescope is going to be observing Saturn, and with the information extracted from the sodium laser guide star, we can correct for the atmospheric effect and get a much nicer picture of Saturn. Is not that cool? Okay, so this is our second type, what we call the sodium laser guide star. So basically, laser guided stars are used as a reference for the adaptive optic systems. They measure and correct the atmospheric effect on the light. There are two different types: the Rayleigh laser guided star that we can generate using a green laser, and the sodium laser guided star that we need to use an orange laser. So anyone can guess which is going to be the next color of laser guided star? Maybe a multicolored one? This is actually not far from reality. So maybe you need to stay tuned for the future talks about laser guided stars and find out about this. So this is what maybe the next generation of laser guided star is going to look like. But how is going to be the next generation of laser guided star creators? Right now, we are a group of people from all around the world, here in Australia, overseas, people from different nationalities, different languages, different backgrounds. We all work together to have our own stars up there on the sky. So if you want to have your own star too, you just need to know that you have to study science. Okay, so this is all for now. I'm happy to take any questions that you have. I would like to first thank everyone for attending this talk. Thank you all to Brad and Brittany, who you don't see her, but she's in the background doing a lot of work. Thank you also to the Auslan interpreter, and to all these amazing women that have sent me all these pictures for me to include in this slide. Okay, so let's go with the questions now. Okay, how does this correct the image? Okay, so we are measuring the atmospheric turbulence, right? And then the deformable mirror will change. So in a first iteration, let's say, the light comes to the telescope. The deformable mirror is flat. So we are going to get a deformed light on the wavefront sensor. This will allow us to measure the turbulence. We'll send the information to the deformable mirror. And the deformable mirror will change the shape to make the opposite shape of the turbulence. So we are going to subtract the turbulence information from the light. And then we're going to get, instead of this blurred image, a much nicer image. Okay, does this laser affect any airplanes flying by? Yes, it does. Actually, these are lasers that are usually with power higher than 20 watts. So just for your reference, one can burn a piece of paper with 1 watt. So if you just propagate 20 watts plus to the sky, and there are airplanes flying by, we are not going to make the airplane explode, but we could get, I don't know, we could get the pilot blind, for instance, blind in the sense of it could lose the vision in a really moment, in a specific moment, and that could cause some damage. But so in order to do that, we need to ask for permissions to propagate all these lasers. So there is, like, depending on the country, there is a standard that we need to use and an authority that we need to ask for permission for. So would yellow laser light also be effective, along with orange and green, since it's in a similar wavelength range? Okay, so one could argue that the laser that we're going to use is orange or yellow. The important part is that the laser has the sodium wavelength, which is 589 nanometers. So we need to actually be at the exact sodium wavelength to be able of exciting these atoms. Any variation in the wavelength would imply that we are not going to excite at all any atom, and then we cannot get this nice spot on the sodium layer. Okay, so you point the guide star at where you want to observe, but does that affect what is observed? Well, you have to point the star out of your field of view of observation. So usually these big telescopes, so we are talking here about telescopes that are maybe 2 meters, 5 meters in diameter. So they are really big telescopes. So we usually point the laser in such a way that the field of view in which we are observing the interesting object, the science object, is not affected by the laser light, because otherwise it would introduce some information that we don't want on our science image. Why are the colors different? The colors are different because they have different wavelengths. So if we look at the spectrum of the light, there are different, every wavelength has a different color. So that's why they are different. So green has a 532 nanometers, and orange or yellow, depending on who look at that, has the 589 nanometers, which is exactly the sodium layer wavelength. And that's why they have different colors. What is the absolute farthest distance you can shine a laser? Well, that depends on if you want to see it. So if you want to see the laser, then the farthest distance to which you can shine it is this 20 kilometers, around 20 kilometers that the atmosphere lasts, because above of that, you cannot see it anymore. In terms of if you want to shine a laser to a satellite, for instance, you can. So you just need to have the proper receiver on the other side to be able of getting that laser. But yeah, you can. It will be bigger because the light will grow, will expand the diameter as soon as it goes up. But yeah, you can definitely do it. And it will be less intense. That's also because it will lose power as in the meantime it's going up. Okay. Why orange and green? Yeah, so those are the colors that are most effective. So in this case, green is the most effective one in the case of seeing the Rayleigh, this reflection on the dust particles. In the case of orange, it's because it's the sodium wavelength. So we really need that one. But there were people investigating other colors. So there was some research using blue lasers, but because they were looking at the different return that they could get with the Rayleigh, but so far those two are the most common ones. Okay, so you can actually change the surface of the mirror. What is it made of? Okay, so the mirror has a metallic coating like any mirror, but the key point is that this surface of the mirror has some actuators on the back. So the mirror surface is really thin. So these actuators can move the surface of the mirror by a certain amount, and that will change the surface. So it's not actually visible with the eyes because the amount is really, really small. But yeah, this really thin layer could be moved with actuators on the other side. How do you make the lasers different colors? Well, there are different techniques of making lasers. it depends on the cell that we are going to use to shine that light. So this is a bit like complicated to explain, but there are really different, like a bunch of different techniques to make lasers. So from semiconductor materials to Raman fibers. Now, for instance, in Macquarie University, they are explaining the possibility. They are exploring the possibility of using diamond to like generate this laser. Whose invention is this? I actually don't know whose invention is this. I know this has been around since the 90s. At the beginning, it was the military research groups who did this first. And then once they released the results to the broader community, astronomy started to using it. How do you make a multicolored laser? Well, so the multicolored laser would be, it would be not a multicolored laser. The glow would be multicolored. So we will have a laser with a certain color, but that would excite different different areas on the sodium layer, and that would produce different fluorescence of these sodium atoms. Thank you again for attending this talk, and I hope you like it.